So the Fourier transform brings with it many useful properties. And when we use the Fourier transform to go from one kind of basis to another, often it's position and momentum space that we're transferring between, or time and frequency, there always is the lurking question of how our basis is changing, including how the size of our basis is changing. So we can think about our basis size as how many phi n we need to describe our system. And we'll see that this question, how many basis vectors we need to describe our system, changes depending on what lens we're viewing our system through. So, for example, we'll look at two different extremes. One of them is the free particle. You've probably seen this example in your undergrad quantum mechanics work. The free particle could be anywhere, right? It's the whole idea of it being free is it's not confined to some region in space. We're just as likely to find it at positive infinity as we are at negative infinity, right? Equal probability everywhere. And so if we're dealing with basis vectors, phi n of x, using our Hermite polynomials, we would need an infinite number of them to describe the position of this particle. However, when we go to momentum space, we would need an infinite number of these. When we go to momentum space, using our momentum eigenvectors, our momentum eigenfunctions, if we need infinitely many of these, it turns out that we can describe our system with just one characteristic momenta. The size of our momentum basis set needed to describe a free particle is one basis vector, one plane wave state. And so we'll see why that's true right now. So let's use our definitions and see what happens. Let's start off, let's work backwards through this one. If we have one momentum that describes our entire system, then we are dealing with a Dirac delta. Our system can be described by the integral of p minus p prime, the integral of our Dirac delta times our function. And just to make things a little bit more straightforward, I'm just going to say we're dealing with a particle with zero momenta, centered at zero. So, if we're dealing with this, then if we wanted to do our inverse Fourier transform to go from momentum space to position space, then our position space representation of the wave function, using our definition from last time, this would be e to the I px Dirac delta of p dp. If we are integrating over p, the integral of any function times the Dirac delta is just that function evaluated at where the Dirac delta is centered. This Dirac delta is centered at p equals 0, right? It's p minus a. That would be where it's centered, is at a. It's 0 in this case. So if we evaluate this, this will be 1 over root 2 pi times e to the I times 0 times x. E to the 0 is just 1. And so it turns out that our position space representation is a constant. In other words, if we were to draw graphs representing these two different ways of looking at our system, one of them f of x versus x, one of them f of p versus p. in the f of x representation, we have a constant. Our system would be a flat line, right? We're just as likely to find it at 0 as we are over here, as we are over here. Everything is flat. However, our momentum space representation was a Dirac delta. So it's 0 everywhere except where it's peaked, right at p equals 0. And so we see that the size of our basis sets are very, very opposite. If we only need one momentum space basis vector, and we need an infinite amount of position space basis vectors. So we could also take the inverse of this system. We could look at a trapped impurity. Maybe we have a system, we have a particular atom where there is an electron that's bound, stuck at one location. If that was true, it turned out we would need an infinite number of momentum states to describe our system in momentum space. The same idea, except the size of our basis is swapped. So this idea of how certain we are about the momentum versus how certain we are about the position might ring some bells, right? This is very closely related to the uncertainty principle. If the size of our basis for one set grows, we're less certain about where we are. We're less certain about the position of our particle because we need more basis vectors to describe it. When we evaluate expectation values, we'll get more terms mixing together. But as one basis set grows, the other one shrinks. The more certain we are about the momentum, the less certain we are about the position, and vice versa. So we should describe some other properties in this sense. If we take the Fourier transform, I'm going to write this big aggressive F right here. This is our Fourier transform operator. If we apply this on f of ax, where a is some variable describing how far we're spreading apart our basis vectors, this is equal to 1 over a times f of p over a. So what this says here, this is a scaling relation, as the distance between our points spreads out in real space, everything is getting squeezed together in momentum space. All of the momenta that we use, we have to push them closer and closer together. And so generally, as we try and squeeze things in one kind of space, they stretch in the other. So this is something you should keep in mind when you're dealing with Fourier transforms going between x and p. If you're in condensed matter, often you'll end up writing this as x and k. But we can also use our Fourier transform to transform between variables like t and frequency, omega. And this is very useful for anyone doing experimental measurements where you get some kind of signal, some kind of periodic signal that has these embedded frequencies. We can take all of these ideas that we had about vector spaces, or we can take functions and signals and decompose them into basis vectors and apply that to signals. For example, if you're operating some probe in an experimental capacity, not an experimentalist, I don't know if you can tell, you might get some signal that looks like this, where we very clearly have some large-scale, long wavelength sinusoidal behavior. And this is just, I don't know, we'll say this is f versus t. Some response versus time. We have some very long wavelength behavior, low frequency, but we also have some very high frequency wiggles that are embedded inside of this bigger curve. So we have this thing existing versus time, And because it's so spread out in time, right, this is certainly not localized, we get this big repeating pattern that stretches and fills the space, more or less. If we took a Fourier transform, which oftentimes experimentally corresponds to either pressing the FFT, fast Fourier transform button on an oscilloscope, or if you're using software, there's a Fourier transform function, FFT, the fast one, embedded in most math libraries. Then this would turn into, I'll draw it down here below, this would turn into our signal as a function of the frequency. And we have very big amplitude oscillations for our low frequency. So we would have a big spike at some low frequency, and at a high frequency, we have much smaller oscillations here. So we'd maybe have another spike like this. And so this is a very useful technique for taking a complex signal and trying to decompose it into a few constituent parts.